What we're going to do today is we're going to start talking about different ways of ordering infinite sets. So start with countable sets, so a set that has the same size as the natural numbers. So one way in which it can be ordered is like the natural numbers are ordered. So like that. But there is a different shape that an ordering of a set of that size could take. For example, you could have countably many items arranged this way and then an extra thing at the end. So notice that these two sets, so the one that's just like that, and the one that has the extra thing at the end, have exactly the same size. They can put in 1-1 correspondence with one another. But the ways in which they are arranged are different. Can anyone give me a different way of arranging a countable set? One very different from any of the other ones I've written down?
1, 1, dot, 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 and then do another 1, 1, dot, dot, dot.
Yes, nice. Very nice. Very nice. Or indeed 3 or 4, or as many as there are natural numbers. So this kind of ordering, the usual ordering of the natural numbers is called an omega sequence. So omega is the last letter of the Greek alphabet. So that's an omega sequence, and what philosophers call a reverse omega sequence is that kind of ordering, but in reverse. So you have countably many things to the left, and then a last thing right there. So that's a reverse. In fact, you can think of the integers, so both positive and negative, as a result of putting together a reverse omega sequence for the negative integers and a regular omega sequence for the non-negative integers. Okay, so what we're going to do next week is we're going to go wild with these orderings. Like we're really going to consider the weirdest and most marvelous orderings in the universe. And part of the reason that's cool is that in order to talk about really big sizes of infinity, so not the teeny tiny ones that we've talked about so far, you need to have orderings in your toolbox. Because otherwise, the infinities we're going to deal with are just, they're so big that we don't have words to describe how big they are. Whereas if we have nice ways of talking about orderings, then we can use an ordering to talk about sizes of infinity. So for example, the ordering you gave is pretty useful. So you can say there's a smallest infinity, which is the infinity of the natural numbers, and then a next one, and a next one, and a next one, and so forth. And then there's one which is, of the ones that are bigger than all those, the smallest, and then the next one, and the next one, and the next one, and then again, and then again. And then by complicating the ordering, you can talk about bigger and bigger infinities. So ordering is going to be important. But today we're not going to go crazy yet. So today we're just going to talk about omega sequences and reverse omega sequences. And the reason I want to do that is because, first of all, I want people to just become comfortable working with these beasts. And secondly, because they are so much fun. So there are zillions of little puzzles that philosophers like, which are based on omega sequences. So they're all of the form, start with an omega sequence or a reverse omega sequence of people or steps or something, and then add in some details, and then look at what happens. So we're going to just talk about a bunch of those. Today's session will be the closest to fun that philosophy can be. So philosophers have party tricks, and these are them. And one reason I think it's fun is that I'm going to talk about a bunch of puzzles, and for some, all philosophers agree about what the solution is. But for others, they don't. So like, I'm genuinely interested in seeing what you guys think and like what seems possible to you guys and what doesn't seem possible. And another reason I want to talk about all these things is that one of my old mentors is basically the most famous living creator of one of these omega sequence puzzles. So he's the guy who came up with Yablo's paradox. So I'll briefly tell you about Yablo's paradox today, and then on Wednesday, Yablo himself will come talk to you guys. And he sent me his notes over the weekend, and they're awesome. Like it'll be so good. So also I want to prepare you for his session because like I don't want you to miss one bit of it. Okay, so let me start with the most famous, but also in some ways the least interesting of the omega sequence puzzles. So suppose that I want to leave the room. There's the exit right there. So all I need to do is walk to the exit and leave. But of course, in order to do that, I first need to reach the halfway point. So I need to make it all the way to here. And then I need to reach the halfway point between this and the door. So I need to make it to there. And then that halfway point, and another, and another, and another. In other words, I need to do infinitely many things before I'm able to exit. But the paradox goes, how could a finite being like myself do infinitely many things in a finite amount of time? Okay, so who can answer that question?
Well, if you took half as much time to do each movement, then the sum of all the times would still be a finite time.
Nice. I think that's right. I think that's the right answer. And I think that for this puzzle, philosophers really do agree that that's the thing to say. So, so we have our omega sequence. So we have the halfway point, and so I'll have this be distance to the exit. So a fourth, an eighth, a 16th, 1/32, and so forth. That's our omega sequence. And then one can say, well, it's true that those are infinitely many things, but let's suppose that this is how long it takes me in seconds to reach each of those points. So say that it takes me half a second to reach the first one, and a fourth, and an eighth, and so forth. Since this series adds up to 1, that means that I'll make it to the door in 1 second. And that's fine. Okay. So far, so good. Okay. Now I'm going to tell you about another omega sequence puzzle, which I think is harder. And this one, too, was designed by an MIT professor called James Thomson. And it's referred to as the Thomson lamp. Lamp. So this is meant to be a desk lamp. And I don't even know if they make these anymore, but apparently he had one that had a button, and then if you say it's off, if you push the button once, it goes on, and if you push that same button again, it goes off, and then on and off, and so forth. So what we're going to do is we're going to create an omega sequence. So say that at noon, our lamp is off. And then at 11:30, we're going to press the button. with the result that the lamp is going to be on. And then at 11:45, we press again. So the lamp is going to be off. And then at 11:50, I don't even know what it is, 15 divided by 750, 52, 30 seconds, I press again, and then the lamp is on, and I keep going. Oh, sorry, I did 11, okay. Say we just started at 11. So here is the question for you guys. At noon, is the lamp on or off?
I'd say it's really an indeterminate state because you're basically asking what's the last number in an infinite sequence of alternating ones and zeros, and there is no last number in that sequence.
I think that that's exactly right. And again, I think that that is an agreed upon solution to this puzzle. So let me just expand on what you said. The description of the case gives us perfect information about what's going to go on with the lamp at all points prior to noon. So if you give me any time between 11 and noon, not including noon, then the facts of the case tell you exactly whether the lamp is going to be off or on. But nothing in the case tells you anything about what happens at noon. In fact, you can think of it as a function which has a discontinuity point. So you have 11, noon, and you go from off to on, to off, to on, to off, to on. And then the function just tells you nothing about what happens at noon. One thing that's weird about the case is that there's no way of completing it without a discontinuity. So there's like no natural stable way of continuing the sequence. But that doesn't mean that the setup of the case is inconsistent. I mean, maybe it's inconsistent if you add in certain laws. Say if you have like a very minimal physics that just guarantees that natural phenomena are going to be continuous in some broad sense, then you can't construct a Thomson lamp. But it really is consistent. One way of seeing that it's consistent is to imagine this. Imagine that you have a version of the lamp such that each time you push the button, it's not just true that it changes from on to off or off to on. It's also true that it reduces its size to half. So suppose that at the initial state, the lamp is 1 meter tall, and then at this point it's 1/2 meter tall, and then 1/4, and 1/8, and so forth. So that series converges to 0. So you could just think that what happens at the end is that there's no lamp. The lamp has disappeared. So that's an example of a case in which it's not off, it's not on. It's rather that it's disappeared. There's no more lamp. Yeah.
I don't know any kind of like mathematical way to prove this or anything. Probably it's not even like mathematically true, but something that I thought of when I saw this is that I think that near noon it behaves very much like the graph of sine of 1 over x.
Oh, it could be. What does the graph of sine of 1 over x behave?
It just has infinite near 0. The graph goes infinitely up and down,
Yeah.
but on both sides of 0, to the left and right actually, like it looks like a normal continuous function, but it just goes infinitely up and down without like, it's just weird.
Right. Well, yeah. So this is definitely kind of like that.
Yeah.
Yeah.
That's what I found.
Yeah. Right. Okay. So here's another weird feature of this case. So this is we've seen the omega sequence version of it, but what about the reverse omega sequence of it? So let me start with a simplified, oh yes, yes.
Wouldn't that be like the Eco-Bomber's paradox?
Ah, very nice, very nice. You are actually one step ahead of me. So let me do this as a warm-up case, and then the next thing we're going to do is the Bomber's paradox. You're right.
Oh, we already did it.
Yeah,
Okay.
yeah, and you'll see how that'll also turn out to be isomorphic to Yablow's paradox. Okay. So here's our warm-up case. So suppose that instead of states of the lamp, you just have a bunch of different people. So there are infinitely many, and they're arranged like a reverse omega sequence. So they're each have to say yes or no, and the last person in the sequence is going to say yes or no at noon. In fact, let me draw this in a more helpful way. Okay, so here we have noon, and here we have 11. So the first person is going to have to answer their question at noon. The second person at 11:30, then 11:15, and so forth. But of course, there's no one at 11, so it's a reverse omega sequence. And suppose first that they all make the following plan. They all say, I'm going to answer in whichever way the previous guy answered. So just imagine yourself being a member of that group. So you occupy some position in here, and wherever you are, there's going to be someone who comes immediately before you. So your answer is set. You have no freedom. So if the person says yes, you're going to say yes. If the person says no, you're going to say no. And of course, that's going to cause the next person to say the same thing. And that's going to cause the next person to say the thing, all the way up to noon. So there are exactly two consistent ways for the sequence to develop. It can either happen that everyone says yes, or it can happen that everyone says no. But which is it going to be? Presumably, it's another example of it's not being determined by the case. And what's weird about it is that it's not determined by the case, even though nobody has any freedom about what to choose. So every single member of the group is going to be forced in their decision. And yet, things could go either way. So how is that? How is it possible for there to be a group of people who have no choice, and yet there can be more than one outcome? And of course, there's a variant of it which is a little more similar to the Thompson case, which is you just say, have each person answer in the opposite way as the person before. So then, again, you have no freedom. If the guy coming before you says yes, you say no. If they say no, you say yes. And then you can ask the question, okay, so what's that guy going to say? Are they going to say yes, or are they going to say no? Nobody has any freedom, and yet it's not determined by the setup what it's going to be. So I think that one thing this teaches us just about the worlds we live in is that it doesn't have situations like these. Because we're used to, so the only sorts of cases that our ordinary theorizing is prepared to deal with are cases in which, if there's a indeterminacy, it's because there is some component of the system that's not fully constrained. Like we're just normally not equipped to deal with a case in which every element of the system is fully constrained, and yet the entire system works in a non-constrained way. Okay, so now let's talk about the Balmer paradox. So the Balmer paradox, too, is a reverse omega sequence. So just to remind you what's going to happen is that you have infinitely many people, and they've each put together a bomb. And let's just say that the effect of bombs is to disable every other bomb. That's the only thing bombs do. And then our noon person has set their bomb so that it goes off at noon. It just has a tamper-proof timer. And that person sets the timer for 11:30. And again, the timer is tamper-proof, and so forth. So the situation we have is this. We know that bomb 0, and that's 0, 1, 2, and so forth, will go off if and only if for all n greater than 0 So bomb 0 will go off if and only if no earlier bombs go off, because if none were to go off, then just the timer will reach the designated time and the bomb will explode. If an earlier one does go off, then the explosion will disable the final bomb. So that's what we have an if and only if. And the same is true for each of the other bombs. So bomb 1 will go off and so forth. So now let me ask you guys the same question I asked you the first session. What's going to happen? So noon rolls around, and what happened? Yes?
I actually don't remember, to be honest with you, like the actual answer, but I just think that no bomb goes off.
That's just what your gut tells you.
I feel like that's what we discussed. I don't remember though.
I see, it's interesting. Unlike the other cases, here I don't think there's a consensus about what to say. So I think that basically here we're on our own. Well, he has a...
I think we showed last time that that there are two consensus, as you said, that the bomb will go off, at least one bomb will go off, or no bomb at all will go off, and we had proofs for each of them. And that relates back to what you said, that there is no consensus here. So the two occasions can happen. Either one bomb goes off or none of them goes off, and both of them have substantial proofs backing up.
Let's do that reasoning. I think that will be very useful. Okay, so let's just consider two scenarios. So scenario 1 is one in which bomb 0 goes off, and we'll just see what happens. And then scenario 2 is going to be one in which bomb 0 doesn't go off. And then that's another scenario, and we'll see what happens. So suppose that bomb 0 does go off. Well, we know from this condition what that means. That means that every other bomb failed to go off. Okay, so that means in particular that the next one failed to go off. But we know that the only circumstances in which bomb 1 fails to go off are ones in which It's not the case that everyone below him failed to go off. And therefore, a situation in which someone below him went off. But that contradicts what we said earlier, because we started with the idea that bomb 0 went off, and therefore that everyone below him didn't go off. So we've proved a contradiction. So in effect, we've proved that this is impossible. Does everyone get that reasoning? So I'm gonna give you guys a few moments to digest, but I'm happy to just say it again. Okay. So what about this case? What about the case in which B0 doesn't go off? Can anyone produce a proof of the kind that I just produced?
If B0 doesn't go off, then since the conditions are if and only if, that means there is some n greater than 0 for which bomb n did go off.
That's right. So we have bomb, I'm going to call it K. So bomb K does go off. So that one goes off, okay?
But the catch then comes from the fact that for bomb K, you can do the exact same proof we did for bomb 0 to show that it did not go off.
Exactly. So if you just look from bomb K down, that looks exactly like what things look like when you look at bomb 0 and see what happens below him. So you're right, it's exactly the same reasoning. So again, we've proved that situation 2 doesn't obtain. But wait, we've proved that bomb 0 doesn't go off. Sorry, that it's not the case that it goes off, and we've proved that it's not the case that it doesn't go off. And that's a contradiction. So actually, you're being very, very generous towards me because the nasty way of putting it is that the conditions are inconsistent. The generous way of putting it, which is the one that you used, is to say, well, look, we have 2 different kinds of arguments, and they point in different directions. And I think that philosophers who take this seriously like the way you put it, because they see it as an opportunity to understand what went wrong. They say, look, it can't be the case that both arguments are right, because no contradiction can be true. So we have a challenge. So let's set ourselves the task of finding where in those arguments we went wrong. And I think it's hard to tell. I think it's generally hard because when you look at bombers individually, there's no reason why they couldn't build their bombs. So just imagine yourself, you're bomber 1. So there you are, you have the equipment. You can set your timer for any time you want. So you just set it for 11:30. Like what's wrong with that? And the same is true for each of the others. And yet, when you put them together, something impossible happens. So it's a little bit like the other cases we talked about, where there's a discontinuity between what happens at the global level and what happens at the individual level. So in the previous cases, the discontinuity was that there was full determinacy at the local level, but indeterminacy at the global level. And here what we have is a situation in which there seems to be consistency at the local level, or possibility at the local level, but no possibility at the global level. Yeah.
You just mentioned how what's going on with each individual bomber is completely possible, but how when you put it all together, it's impossible. But I just think that's because we're putting it all together in an impossible way.
Okay. Can you say more? I think that's interesting. Say a little bit more. Yeah.
That, it's impossible to have infinitely many bombers who all plan to set their devices to infinitely closer times to 11 a.m. Like all of that is completely impossible, and that's why when you take several completely possible events and put them together, it makes it impossible. Is because you're putting them together in an impossible way.
I like that. Yeah. So there's got to be something right there, because it's true that individually each of them is possible. So somehow you can't put together infinitely many perfectly possible things. I guess that the real challenge is to get a better sense of why. Like, why does it go wrong? I mean, one thing I could say is, well, because otherwise you get this puzzle. But it would be nice to like be able to say in a little more detail, just what's so bad. Because you say, well, each of them seem fine. You had a...
Could you have a problem with your second proof in the setup that you're trying to answer a different question? Because they're saying, essentially, which bomber goes off instead of does a bomb go off or not, right? So, like, you're claiming, okay, I know what bomber went off is bomber K, but that's not really a question we can answer with our setup. It's just whether or not a bomb does go off is, our original intent.
I mean, it's true that in the second argument, there's this unidentified bomb K. But I think that the way to think of it is to just say, it doesn't matter who K is, we're going to get the same result anyway. So how about this way of recreating the argument? So you just say, as you point out, what we want to know is whether bomb 0 goes off. That's our question. And then we say, well, let's just explore what the world would have to be like under the assumption that it doesn't go off, just to see what it looks like. And then we say, well, if it doesn't go off, then by this condition, some other bomb needs to have gone off. I'm going to call it K. Of course, I don't know which one it is, but it won't matter because, like, whatever it is, I'm going to reach the same conclusion. And then we say, well, but if that one did go off, it's because nobody below her went off. So then we've reached a contradiction because we can just recreate this reasoning.
We could maybe model this situation by like the assumptions that we're using, as well as like the situations that could happen for each bomb. So we could maybe make like a 2 by like infinity grid of like all the states that we could have, where like each column would be like for bomb N, and then the each row would be bomb, it either goes off or doesn't go off, or doesn't go off.
That's right. So 0, 1, 2, 3, 4, and then on or off, or so it goes off or doesn't go off. Yeah.
And then we can rule things out based on what we have from the problem statement. Oh, nice. And then what we see is that sorry, could I see the board behind that one again? Yeah. We could see that bomb 0, like by our time argument, bomb K. We rule out the possibility that bomb K goes off by like the increasing pollution argument, and then but for the other state to be true, we need that one of the boxes on the left column must be not crossed off. And so now we've put together a set of boxes that just don't fit together.
No, I like it. I like it. We just have inconsistent constraints on our array. You have some conditions that force you to rule some out, and other conditions that force you to rule other ones out, and you're just left with nothing. That's right. That's right. Yes.
I'm not sure like the best way to word this, but could this be like sort of like seen as a problem with trying to sort of relate like events causing other events, and sort of relating that to our general notion of like continuity and like numbers? So like you try to define like a set of events. Yeah.
That's right. There is a connection, and in fact, we sort of that emerged in the first session when we talked about a variation of this, which had to do with walls. So let me put that on the table, and then I can come back to what you're saying, because I think it's important. So suppose that rather than times, we have distance. So I'm going to erase these times, and then I say, okay, this is a meter away from this line, and that's half a meter away, and a fourth of a meter away, and so forth. And then each of these people build a wall. So there's a wall there, and a wall there, and a wall there, and a wall there, and a wall there. But of course, there's no wall at the exact endpoint. And then I fire a bullet And let's just assume that each wall is capable on its own of stopping the bullet. So we say, well, what's going to happen? We say, well, if nothing stops the bullet, we're inclined to think, well, the bullet is just going to keep going. But it can't make it beyond this wall because that wall's going to stop it, and it can't make it beyond that point because this wall's going to stop it, and it can't make it beyond that. So we say, well, it can't make it beyond this line. Because even if it just makes it a little bit, then it's already too much. Like there's already walls that should have stopped it and don't. So then, okay, we have an argument for thinking that the bullet is not going to make it past that line. But then what stops it? Because at the line, there's no wall. So let me now go back to what you were saying, because I think you're right. This sort of construction puts pressure on our ordinary ways of thinking about causation. Because we're inclined to think that if a bullet stops, something stopped it. And here we have a case in which we know that the bullet has to stop, but we have nothing to stop it. So again, I think that the lesson of this is that there's a certain sense in which the concepts we use to think about our world are parochial. They're well designed for the kind of world we live in, but they just wouldn't work when we had situations like those. We would need a different way of thinking. And maybe that's all there's to the paradox. So in order to diffuse the problem here, all we need to say is reject the idea that if a bullet is stopped, it's stopped by something. That'll do it. And in the Bommer's paradox case, you can say reject the idea that if individual events are possible, the result of putting them together is going to be possible too. That'll do it. So maybe all we need to do is recognize that if you move to a less constrained world, you have to give up principles that seem very, very natural.
So another thought is maybe instead of thinking of this as a whole bunch of discrete things, could we think of it more like probability density, where any given probability has 0, but maybe we should be looking at sort of like areas or ranges instead?
Oh, I see what you're saying. Okay, I like this because so we've seen examples in which we know for sure that some point on the line is going to be selected. But for each point, you say, well, how likely is it that this is going to be selected? The answer is, well, 0. So we have a failure of this kind because, well, in that case, it's a failure of additivity. It's not the case that the probability of the entire line is a result of adding the probabilities of the given points. You know, I like that. I don't have a precise way of putting it generally. But it does seem like when we move to infinity, there's certain continuity failures that we're going to have to deal with. And I think the challenge is just they're going to be there. We're not going to be able to avoid them. So I think that the challenge is just to find a theory that is able to handle them in a way that keeps everything under control. And I think that in the case of probability, we have such a theory. Like, we know there's going to be weirdness, but we know how it works, and it's fine. Lebesgue measure. And in this case, I think it's less clear. I just think that we haven't developed the tools. And I think that is like this open problem. So like if anyone can come up with like a way of doing what Lebesgue did for measure, but for these continuities, for these as continuities, then that's like this new branch of mathematics. Okay, so one last question, and then we'll move to Jaap.
I'm just kind of thinking, like, is there, going back to the original Bommer problem, is there really a huge issue if the system is inconsistent? Because it's kind of a extension. You can set up like a system of true-false things such that, like you can set up 3 such that pairwise any 2 are consistent, but all 3 together are inconsistent. And so it's just kind of an extension of that to infinity, where any finite subset is consistent, but all infinite are inconsistent.
I think that's right. So that is definitely a feature of the case. I think you're right that you have cases where you just have finitely many items that generate the paradox. The reason I think this is harder is because I feel like in some of the others, you can sort of see what goes wrong. It's like, I don't know, the way I think of it, it's like each person puts little conditions on everybody else, and you can see how, like, if the conditions pile up, then things are going to explode. What puzzles me about this is that I feel like I'm not able to say anything illuminating about where the problem emerges from, over and above just saying, because you get this puzzle. And that's what I don't like. So we want, it's like we don't want to address the paradox by just saying, do whatever you need to do to avoid contradiction. Like you need a theory of what it is that causes the problems, a general theory, and say, look, once you've addressed this, then no problems of this kind are ever going to emerge, kind of like Lebesgue did with measure. And that's what I feel like I don't. That's what I feel like I don't have. Okay, so I want to briefly tell you about Yablow's paradox, just because you're going to meet Yablow on Wednesday. It'll be cool for you guys to know about it. So what Yablow did is he was thinking in a very different context. He did for truth what the Baumler's paradox does for explosions. So what he does is he says you have not infinitely many bombs, but infinitely many sentences. And you say, sentence 0, not will go off, but is true if and only if, for any n greater than 0, sentence n isn't true. And then S1 is true if and only if Sn isn't true. And you just keep going. And I think this puzzle is even more interesting than the Baumler's paradox for a couple of reasons. In the case of bombs, like, you know, you need to imagine that people like construct these bombs, or they have these timers and so forth. And in this case, there's nothing of the sort. Because just let S0 be the sentence that says, everyone below me is true. And let S1 be the sentence that says, everyone below me is true, and so forth. You know, they're just these sentences. They're already part of our language. And yet you get the contradiction. So this is like saying, I'm going to present you with the Baumler's paradox, and moreover, I already have the bombs. They're in my warehouse. And another reason it's interesting is because it shows that a family of solutions to the liar paradox can't work. At least they can't work without help. So the liar paradox is a sentence that says, I'm not true. And you say, what? Okay, so is it true or not? If it is true, then what it says is true, but it says it's not true. And if it's not true, and then you have a similar argument. Now, often people say, well, the problem with that sentence is that it's self-referential. So it talks about itself, and whenever something that talks about itself, you're going to get problems. But wait, here we have no sentence talking about itself. All sentences just talk about people below them. So you have a version of the liar paradox that does not involve self-reference. And that's why Yablow's paradox is so famous. Because it shows that the semantic paradoxes are just deeper than everybody thought. You had a question? Oh, sorry. Okay. Okay. So I'm going to end with a final example of paradoxical omega sequences. And this one is my favorite of all. So imagine this situation. Again, an omega sequence. This time you have an omega sequence of people. So you have person 0 and person 1 and person 2 and so forth. And the devil approaches them and says, I'm going to offer you guys a deal. So what I'm going to do is I'm just going to approach each of you, and you can just say yes or no. And then after I'm done, I'm going to count how many yeses I got. And I'm just going to give each of you as many gold coins as yeses I got. So if 44 of you say yes and the rest say no, then I'm going to give each of you 44 coins. But should infinitely many people say yes, then nobody gets anything. Okay, so then imagine that you're one of these people, and it's your turn, and of course it's going to happen in order. So first person 0 is going to be asked, and then person 1, and so forth. And it's, as usual, it's going to happen faster and faster, so that by a certain time they're all done. So now suppose that you're person K, and you say, well, shall I say yes? You say, well, look, two things can happen. Either everyone ahead of me, either infinitely many people ahead of me are going to say yes, in which case, there's nothing I can do. Like, we're going to get nothing anyway.
Whoa.
Or finally many people ahead of me are going to say yes, in which case I should say yes, because that way all of us are going to get an extra gold coin. And that seems like a rational argument, but of course if everyone reasons that way, nobody gets anything, because everyone says yes. Yeah.
I'm just extremely confused. I don't think that's a rational argument at all, because when you say you say before me, if infinite many people are going to say yes, then we're not getting anything anyway. What if you say no? What do you mean? If you say no, you've stopped that. I don't. It's not like you have no right.
Let's consider this version of the case because I think it's cleaner. So, just as before, except that the devil separates all the people, puts each of them in a soundproof room, and just asks them each to make their decision individually without communicating. So then you know that whatever you decide cannot possibly affect what others decide. So just people are going to be on their own in the room. And then you say, look, I can't possibly harm people with my answer, because one yes can't be the difference between going from the finite to the infinite. But I can help them, because if only finally other people say yes, then we're all going to get one more gold coin. So I should answer yes. It's either we all do better or we don't do any worse. Of course you should say yes. But then if everyone says yes, nobody gets anything. Okay, we're out of time, but one last question.
Where is infinity?
Where is it? Say more. What do you
If you are really, really very critical about it, we have never defined infinity to be 1,000 or 10,000 or anything. So the devil can always have a winning strategy that any number you guys choose was his infinity.
Oh, no. But fortunately, the devil has taken paradox at infinity. So the devil knows. The devil knows that what it means to be infinite in this context is just for there to be as many yes answers as there are natural numbers. And just like you guys, he uses 1-1 correspondence to measure these things. So it's interesting because although we have developed some pretty nice tools to thinking about infinity, there's still some remaining issues that we don't know how to deal with. Okay, so don't miss next session because it'll be Steve Yablo and it really will be awesome.